Welcome to section 3.2, measures of dispersion. So in chapter 2, we talked about the shape of the distribution. In 3.1, we talked about the central tendency. And now we're going to talk about the dispersion, which is also called the spread, or another word for the spread. So first we're going to talk about why it's important to include all three characteristics: shape, central tendency, and spread. And how we're going to do that is we are going to draw two histograms that both have the same mean and the same shape. So let's say they have mean at 50. They have a mean at 50, these two histograms, and they're both bell-shaped symmetric. But let's say the one on the left right here has more spread. All right, so it ranges maybe from like 10 to 90. And then over here, this one has less spread. Maybe something just like this histogram. Whoops. And we'll just say like maybe it ranges from 30 to 70, something like that. All right, so we're looking at these. They have the same mean, 50. They have the same shape, bell-shaped. But the spread is different, and so we're getting very different graphs. So the one on the left, we could say, just for now, it has more dispersion because there's more spread. So the data is more spread out, it's more dispersed. Here, between 30 and 70, it's more compact. It's less spread out, less dispersion. Okay, and we're going to figure out numerical ways to measure dispersion. And what we're going to consider in this section is the range, standard deviation, variance, and later on in chapter 3 we'll look at the interquartile range. But the most basic type of dispersion is range. That's how much the data is ranging. So we do it highest value to lowest value. So in our two examples above, the one on the left, we said the highest value was 90 and the smallest was 10. And so that range would be 80. And then the histogram on the right, max value minus minimum value, the range would be 40. Okay, so there you go. So the range isn't ideal. For instance, if we had one super extreme value, for instance over here, if we just had one random value at 150, that would throw this whole thing off. And we would think that the range is high, that must mean more dispersion. But really what it is just that one value all the way over at 150. So a better way to measure dispersion is a standard deviation. That standard is really a mean deviation. So it's the mean deviation. Deviation from what? Deviations from the mean. So in other words, the standard deviation is a measure of how much the data deviates from the mean. Okay, so let's look at some formulas. Again, population, remember we use Greek letters. So Greek S looks like this, a fancy O, and it's called sigma. So population standard deviation is sigma. And for a sample, remember we use our Roman letters, so just the letter S. So S stands for sample standard deviation. All right, and now let's look at our formulas. So for a population, we are going to look at, well, let's go back up to our graph that we made up here. Okay, so we see that the mean is 50. And then let's say we have one observation here. We'll just say maybe it's like 70, something like that. So there's a deviation from the mean. So this thing in green right here would be the deviation. And let's see, it looks like it's about positive 20. All right, so this would be a positive 20 deviation from the mean. All right? And standard deviation, we would look at all the observations, add them all up, and divide by the amount of observations. That would be the mean deviation. So for instance, over here, let's say we have a 30. Again, we would ask ourselves, what's the difference between 30 and the mean? What's the deviation of between 30 and the mean? 50. It's still 20, but do you see how 30 is less than 50? So it would actually be negative 20. All right, so that's the first part. Let's go down to our formula. So let's call xi the observation. So for each observation, for each observation, we'll just call it xi. There'll be capital N observations. We're going to look at the difference from the mean, and that's the deviation. Okay, the thing is, because all the positives, well, we know the mean is the physical middle. We saw that in section 3.1, the physical middle. So all of the positive deviations are going to balance out the negative deviations, because that's how the mean works. So if we add them all up, we're going to get 0. We can't do anything with that. So to make all the deviations positive, one thing that we could do is we could square the deviations, because a squared number is always positive. All right, so that's what we're going to do. Remember, we use this epsilon for sum. So we're going to add up all the squared deviations. And remember, it's the mean deviation. So we divide by the number of observations, which is capital N. Finally, we're not done yet. Because we squared the deviations, to counteract that, we're going to take the square root. Okay, and then S has a similar formula. We're going to take the square root of the sum of the deviations squared. Whoops, I was going to write mu, but the sample mean, remember what it is? X bar. Going to square that. And then instead of dividing by n, we actually divide by n minus 1. All right, and we call that, when we divide by n minus 1, the reason why we do that is because we have n minus 1 degrees of freedom in a sample. And let's look at the formal definition. So the first n minus 1 observations have the freedom to be whatever they wish, but the nth value has no freedom. It must be whatever value forces the sum of the deviations about the mean to equal 0. So I like to think about bringing a dozen donuts to work. If you bring a dozen donuts to work, how many people get freedom to choose? Well, the first person can choose from the 12 donuts. They choose one. The second person comes in, how many donuts are left? 11. So they can choose. The third person comes in, how many donuts are left? 10. All right, et cetera, et cetera. The 10th person comes in, how many donuts are left? 2. They can still choose. Oh, excuse me, that's the 11th person. The 11th person has 2 donuts to choose from. But then what about the 12th person? No freedom. They're forced with the last donut. So that's something similar. So in that donut example, how many degrees of freedom did we have? 12 minus 1 is 11. 11 people had a choice. The last one, the 12th one, did not have a choice. Okay, so that's why it's called that. We just really use it. That's how we explain the n minus 1 denominator. And then finally, how do we interpret the standard deviation? The greater the standard deviation, so the bigger the standard deviation is, the greater the spread. So in our example up at the top, which histogram would have a bigger standard deviation, the one on the left or the one on the right? The one on the left would have a bigger standard deviation. So because there's more spread, we're going to write bigger. I'm going to abbreviate standard deviation as SD. You can also use sigma or S. Okay, so let's do an example by hand, and then we'll see. The standard deviation calculation is tedious, so we're going to only do one example by hand. I'll show you how to do it on the calculator, and then you can choose from that point out, but I recommend using the calculator. So we have a very simple sample. First, standard deviation from the mean. We'd have to know what the mean is. So we would come in and figure out the mean of our sample. So we would add up all the observations. After we find the sum, we divide by 1, 2, 3, 4, 5 observations, and the mean is 11. Our sample mean x bar is 11. So now here's all our data values in our table, and we're going to figure out everyone's deviation from the mean. So for instance, 20 is our first observation. How does it deviate from the mean? By 9. And then 13 minus 11, how does it deviate from the mean? 2. 4 is below the mean. It's less than the mean, so we get negative 7, etc., etc. All right, so these are just our deviations. All right, and then let's illustrate this point. What happens if we add up all the deviations? Well, 9 plus 2 is 11. Minus 7 is 4. Minus 3 is 1. Minus 1 is 0. So just kind of taking this side route really quick, if we add up all the deviations, it's 0. And that's because the mean is where the histogram is balanced. So how do we get past that? Remember, we square the deviation, so the sum doesn't end up being 0. So let's square all of the deviations we just found. So 9 squared, 2 squared, negative 7 squared, negative 3 squared, and negative 1 squared. Okay, so we have the square deviations. Now we're going to find the mean of all the square deviations. So we have to add them up. So 81 plus 4 plus 49 plus 9 plus 1. That's this symbol right here, the summation. And then normally we would divide by the sample size, but we're going to divide by the degrees of freedom. So our sample size is 1, 2, 3, 4, 5 observations. So we're going to divide by 4. Okay. And then finally, remember to counteract squaring the deviations, we take the square root. And that's the last step we need to find the standard deviation by hand. Okay, and so the standard deviation is 6. If this is a real example, I just want to make a note. Remember central tendencies, so section 3.1, and standard deviation has units. So please include your units, like minutes or feet, something like that. Please include units on the exam. You get a point for remembering the units. Okay, so while we were doing this, we actually came across another definition, another measure of dispersion. It's called the variance. The variance of a variable is the square of the standard deviation. So it's essentially just the stuff underneath the square root. So this 36, before we take the square root, that is your variance. And here's our notation. This is coming from a sample. So we can use S squared. If it was a population, we would use sigma squared. So that's the variance. All right, so food for thought. I'll let you guys digest that, see how well you were able to follow along with the lecture. We went over all of these answers together at some point so far. And now we're going to see how to use our calculator. Because again, that was a pretty tedious calculation, and the sample size was just 5. This sample size is 6. 1, 2, 3, 4, 5, 6, 7. Excuse me, it's 7. So that would be 2 more deviations we have to calculate. So let's use our calculator. It's going to be calculator dependent. So first of all, they ask us to calculate the range. So we have to find the maximum value minus the smallest value. Looks like 282 is the maximum value. What's the smallest? 257. All right, so let's put that in our calculator. And we get 25. And then how do we get full credit on an exam? We remember our units. So 25 minutes. All right. And now let's see, this is a sample. So what's the sample standard deviation? What symbol do we use? S. So here's how to find S. And we'll make a short video in just a second. But how we find S starts off the same way as finding the mean and median. So if you remember, we have to put our data into a list. And then how we find the mean is we hit the Stat button, go to the Calc tab, and the first option is our best friend, 1 var stats. All right, so we'll see that in the next video. And we'll also see that there's 2 symbols to use. And let me write it down and so I can include units while we're together still. S for sample standard deviation. Remember, we're dividing by n minus 1, so 7 minus 1. It ends up being 8.43. Full credit, 8.43 minutes. Good. All right, so that will come in just a second following this video. The last thing we're going to look at is the empirical rule. The empirical rule is only to be used when we have roughly bell-shaped data. All right, so if we have bell-shaped data, the empirical rule tells us how the data is dispersed. And how they do it is this. They tell us the percentage of data that lies within so many standard deviations from the mean. All right, so let's look at this little setup we have here. So here's our roughly bell-shaped distribution. And right here we have the mean, mu, so this is a population. So from the mean, if we add a standard deviation, sigma, and we subtract a standard deviation, they're saying 68% of our data, so most of our data is within 1 standard deviation. So that's where that height comes from. Height is frequency. Okay, so within 1 standard deviation, 68% of our data is with 1 standard deviation. And remember, bell shape is symmetric. So that's why we can divide 68 in half. So actually 34% is on each side. If we go out 2 standard deviations, so if we subtract 2 and we add 2, 95% of the data is within 2 standard deviations. And then finally, the empirical rule tells us about 3 standard deviations. 99.7% is within 3 standard deviations from the mean. All right, so that gives us a good idea of how standard deviation behaves. So look at all these other numbers. So we have all this nice symmetry. They filled in some numbers for us. For instance, let's see, 95, I'm looking at 2 standard deviations, 95%. What's 95 divided by 2? 47.5. Okay, so we know 47.5 would be in 1/2 because of all this nice symmetry. So 47.5 would be here, and 47.5 would be here. And it all adds up to 95. Okay, so that's how they were able to get this 13.5%. All right, because 47.5 minus 34 is 13.5. Likewise, let's consider our tails. So 99.7% isn't all the data. What's left over? 0.3% is farther away than 3 standard deviations. So 0.3% fall outside 3 standard deviations. And because of symmetry, we have to divide it evenly in the tails. So 0.3 divided by 2 is that 0.15%. So that's how they're getting that final percent. Okay, so that's how we are breaking up all the parts of the curve. The actual empirical rule is just this part that we have highlighted in red, blue, and green. That's the empirical rule. So let's see how we're going to use it. So one measure of intelligence in the standard or the IQ scores, and how they're distributed is they have a bell-shaped distribution with a mean of 100 and standard deviation of 15. Okay, so that's kind of our key word, bell-shaped, because we know with bell-shaped distributions we can use the empirical rule. And the empirical rule deal with percentage of data within certain standard deviations. These are keywords. Keywords are important in this class. This is telling us to use the empirical rule, because we're asking to find percentage of data within certain values, and it's roughly bell-shaped. So let's create our curve. It's roughly bell-shaped, so I'm not going to do the histogram bars, I'm just going to do the curve. So roughly bell-shaped means the mean would be right here. What is the mean? 100. And this is what we have to do for these types of questions. We have to figure out the bell-shaped curve. So let's add and subtract standard deviations, because that's what the empirical rule is. We go 1, 2, 3 standard deviations up, and 1, 2, 3 standard deviations to the left or down. All right, so a standard deviation is 15. So let's add 15 each time. So there's 1 standard deviation away or up from the mean. There's 2, kind of running out of room, and then 3 standard deviations would be 145. All right, and then going down, 1 standard deviation away, where you have to subtract 15 now, 85. Subtract a standard deviation again. Subtract a standard deviation again. Okay, so that's our setup. Let's see what part A is asking. They want to know the percentage of people who have an IQ score between 70 and 30. All right, well, here's 70, and 130. And there's 130. And let's see, we have 1, 2 standard deviations down, 1, 2 standard deviations up. Well, according to our empirical rule, what percentage of data lies within 2 standard deviations from the mean? The empirical rule says 95%. So that's your answer. 95% of people have an IQ score between 70 and 130. Let's see what's next. What percentage of people have an IQ score less than 30? All right, so let me highlight. Less than, 70. And greater, so less means to the left. Greater than 130 means to the right of 130. All right, so essentially it's everything left. So if 95% are in the middle, what's left over in the tails? Well, 100% minus 95%, it has to be 5% is left over. 5% is left over. And then we do it one step farther. What percentage of people have an IQ score now just greater than 130? So before the 2 tails added up to 5%, what happens if we look at just 1 tail? Well, it's symmetrical. So we have to take that 5% and we divide it evenly amongst the 2 tails. So the stuff that's greater than 130, whoops, I'm thinking decimals, it's going to be 2.5%. All right. So let's look at another example. You guys are going to do this one on your own. Notice the key words. We talk about bell-shaped distributions, with means and standard deviations, and we're answering questions about percentages between values. That tells us to use the empirical rule. So we'll go ahead and push pause and see how you do. Okay, so I recommend just, again, kind of sketching out the situation. It's bell-shaped, so let's use this. The mean is 515. And we're going to add and subtract standard deviations. So let's add, I think we just need to add 2 standard deviations for this. So I'll just do that in the name of space. And a standard deviation is 114. So if we go 1 standard deviation up, we have to add 114. So 515 plus 114 is 629. Let's go 1 more standard deviation, sigma. It is a population. And we're looking at 743. All right, and then going to the left, so values less than 515, I'll use a different color. We're going to have to subtract sigmas. Subtract 114. So we're looking at 401. We'll go 2 standard deviations away, so we're going to subtract another 114 to get 287. All right, so let's see what the question's asking. So part A, what percentage of SAT scores is between 401 and 629? All right, well, 401 and 629 are how many standard deviations away? Just 1 standard deviation. So according to our empirical rule, 68%, approximately 68% of the observations are within 1 standard deviation. So there you go. We're looking at 68%. And now something similar, what percentage of SAT scores is less than 401? So this area right here, less than 401, and then greater than 629. So to the left of 401, to the right of 629. Well, if this is 68%, what's left over, right? So we have to look at 100% minus 68%. And that will tell us what's on the outside of that 68% chunk. So 32%. Okay, and then finally, what percentage of SAT scores is greater than 743? Oh, they're being tricky. So greater than 743 is just this little chunk. Okay, which is 2 standard deviations away. So let's draw a quick picture. We're 2 standard deviations away now at 743. So according to the empirical rule, 95% of the data is within 2 standard deviations away. So that means what's left over in the tails? What's the opposite of 95%? 5% more will get us to 100%. So that green part that in the tails is 5%. So that means how much is in each tail? 2.5 and 2.5. We divide up 5% into 2. So the solution is 2.5.